Hello everyone, my name is Oostvogels and I'm currently working my PhD at KU Leuven. Today I will be presenting a paper entitled Zero Wire, or a deterministic and low-latency wireless bus through symbol-synchronous transmission of optical signals. I know that's quite a mouthful, so before diving into the nitty-gritty, I'd like to quickly set the scene. Alright, I think most of you will recognize what's being shown in this picture. This is a car assembly line. Now, what you should focus on in the context of this presentation is that this kind of complex industrial environment today is packed to the brim with sensors, actuators, and compute nodes. For example, a set of robot arms will be equipped with motors that drive their position and orientation, sensors that measure their position and operating conditions, and finally control nodes that close a low-latency feedback loop between sensing and actuation, making sure arms go where they need to go and do so without, for example, crashing into objects they're not supposed to be crashing into. So now we've got all of these devices embedded in and scattered throughout their environment while having to communicate with each other. So the question really becomes, and in fact that is one of the questions we're trying to answer in this paper, well, how do we network all of these little devices together in such a complex low latency environment? And the conventional answer to that question is wired networks, in particular bus networks. In a bus, all nodes connect to a single shared set of wires. Two nodes that wish to communicate and simply reach out to each other through the shared bus line, as shown in the figure on the left-hand side of the slide. This approach works great, because it's fast. Signals propagate through your cable literally at the speed of light. Moreover, it's reliable. If you properly shield your cables, your network communicates through a medium that essentially no one can interfere with. Cables have one important disadvantage though. Running cables through a complex environment is difficult and therefore expensive. You need to plan, deploy and maintain a giant mess of cables, which ends up costing you a lot of money. Running a cable through an industrial plant, for example, typically costs you on the order of hundreds to thousands of dollars per feet of cable. And that is of course where the promise of the wireless Internet of Things comes in. If we can somehow get rid of these cables by replacing them with wireless connections, we can do a lot more fine-grained embedded sensing and actuation at a much lower cost. In this context, industrial bus networks are typically replaced by wireless radio mesh networks. The way they work is shown here on the slide as well. We've got a bunch of nodes, each of them equipped with a reasonably short-range radio. If a node A and the node B then want to talk to each other, intermediate nodes will in general assist by receiving, storing, and eventually forwarding the message along a routing path. This approach has a few consequences, namely that we need to do routing and that we need to do medium access control. Routing means that we need to somehow keep track of which nodes are where to tell messages where to go. Medium access control means that we somehow need to prevent two nodes that are geographically close from transmitting at the same time, because if they do, their messages will interfere and get garbled. The introduction of these two additional abstraction layers makes radio meshes a lot slower than their wired counterparts. Latency, so the time it takes for a data frame to propagate from sender to receiver, is typically on the order of seconds and highly variable. And that is a problem. The use cases envisioned at the start of this presentation, and as shown on the slide here, there are more, critically depend on low and deterministic latency. Applications with tactile feedback, for example, may require deterministic end-to-end latency down to less than 1 millisecond. If we today want to replace wired control with a wireless solution, we're simply out of luck if our application has sufficiently stringent latency requirements. And that is where this paper comes in. We introduce a wireless mesh network that behaves like a wired bus from a performance point of view. For example, we'll demonstrate how to communicate 2-byte frames across 4 hops in less than 1 millisecond, and how to achieve wire-like features, such as deterministic goodbye irrespective of contention for the network. A distinguishing feature of the network that we introduce is that it relies on free space optical transmission, so we use LEDs to transmit data instead of radios. As such, we also contribute to the field of optical wireless networking by proposing a solution for the range and directionality limitations researchers encounter there today. Let's have a slightly more in-depth look at that contribution. In fact, it consists of 2 parts. First, we propose a novel networking paradigm called a symbol-synchronous bus that makes a wireless mesh network behave like a single wire. Secondly, we instantiate the paradigm within a physical platform called Zero Wire and evaluate its performance on a 25-node testbed. Let's start with the paradigm. We propose a model in which peripherals, so IoT sensors and actuators, transmit and receive data by pointing an LED and a photodetector towards a canopy of relay nodes. These relay nodes are where the magic happens. They form a mesh wherein any node immediately relays any signal it receives. thus providing end-to-end connectivity across many hops at low latency. Of course, immediately forwarding any received signal is kind of a vague notion, so let's make that more concrete. The figure on this slide contrasts symbol-synchronous buses to more conventional networks. As you can see, data frames consist of physical layer symbols. In regular routed networks, nodes receive a full frame consisting of many symbols before eventually retransmitting it. To save latency, you should parallelize that process as much as possible. In fact, that is what popular research topics in the IoT networking field are trying to do. Synchronous transmission, for example, synchronizes concurrent relays of a full packet to avoid medium access control overhead between potential forwarders. Symbol-synchronous buses take things a step further. Relay nodes in the canopy relay any symbol they observe while that symbol is still being transmitted, without waiting for the completion of addressing information, preambles, message identifiers, and so on. We'll demonstrate that this approach makes a network behave exactly like a wired bus. This is easier said than done. There are very good reasons why conventional networks don't immediately forward messages they receive and wait, for example, for addressing information. In fact, if you try to implement this symbol-level parallelization, you end up with two major challenges. The key innovation of symbol-synchronous buses lies in the way these challenges are addressed. Let's go through them one by one. The first complication is illustrated by this picture. If nodes blindly relay any signal they observe, and their neighbors do the same, signals will keep circling back and forth indefinitely, keeping the network busy forever. If you want to build a stable network this way, you've got to have a way to break feedback loops. We address this problem by imposing a constraint on the timing of transmissions and relays. In particular, we make sure a relay node only receives the next symbol to be relayed after all of its neighbors have started relaying the current one. In other words, we use symbol durations that are slightly longer than they have to be from an electrical engineer's point of view. Symbol duration is stretched to leave time for the effects of a relay step to stabilize. This is illustrated in a figure. If node A here in the middle is relaying, P defers its transmission of the next symbol, the square, until B has transmitted the current one, the circle. P's symbol boundaries then serve as a demarcation point between old and new data, since only the latter needs to be relayed again by A. We refer to this timing constraint as symbol synchronicity. Intuitively, in a symbol synchronous bus, symbols propagate through the mesh like a rapidly moving wave, while symbol synchronicity makes sure nodes latch onto the right wavefront. We shed some light on this principle during our demo later today. Alright, that's how we tackle the first complication in our parallelization exercise. Let's get on to the second. As suggested by this slide, the second complication is not cringy stock photos, but interference. In a symbol synchronous bus, all relay nodes are transmitting at the same time. All of their signals interfere. Nodes that want to relay a signal or receive the data that it conveys must somehow make sense of that mess to refer the original signal instead of the amalgam of all interfering relays. This is where optical transmission comes in. To understand that, we must have a look at a crucial difference between radio-based and optical transmissions. Radios transmit data by generating a carrier wave and modulating its low-level properties, its phase, its frequency, its amplitude, and so on. When multiple radio signals interfere, this garbles the transmission in unpredictable ways. Oscillators used to generate the wave will have slightly different frequencies, resulting in beatings in the combined signals. Moreover, concurrent transmissions will sometimes and at some receiver locations have a phase offset that leads to destructive interference, and not in others. Optical wireless networking, by contrast, does not encode information in the low-level properties of a carrier wave. We modulate the intensity of an LED, so we're looking at the power envelope of the underlying electromagnetic wave. Moreover, LEDs are incoherent emitters, meaning that they keep a consistent phase for only a very short period of time. These two aspects result in the fact that interference patterns between optical transmissions are somewhat predictable. If you take two LEDs and let them transmit the same intensity signal at the same time, a receiver will simply see that very same signal with a higher intensity. The same is not true for radio transmissions. Symbol-synchronous buses exploit this property by designing modulation and demodulation logic to allow nodes to pick up on the next symbol in a transmission among many relayed versions of the same signal that slightly lag behind it in time. In this kind of network, modulation, medium access control, and forwarding become a joint problem. It is this bifold approach that allows symbol-synchronous buses to parallelize retransmissions in a mesh network down to the very first symbol of a frame. This approach, and the resulting bus semantics, distinguish it from other techniques and systems found within the state-of-the-art, such as cut-through forwarding or cooperative relaying. The paper contains an in-depth discussion of related work, comparing our system to, for example, Widom, Zippy, and Glossy. Of course, the next thing we gotta do is actually instantiating this scheme. We need to design a transceiver that somehow complies with the symbol synchronicity time constraint and that exploits interference patterns of a concrete optical modulation scheme to deal with interference. The zero-wire platform introduced in our paper details one solution. For zero-wire, we somewhat arbitrarily choose to solve these challenges for an on-off gain-based modulation scheme. This allows IoT sensors to send data through the network simply by toggling an LED on and off at regular intervals. We then design a transceiver that allows relay nodes to participate in a symbol-synchronous bus for this modulation scheme. The easiest way to understand the transceiver is to think of it as a set of interconnected state machines that are repeatedly updated in sequence to receive and relay data. The transceiver interfaces with an LED and a photodiode to transmit signals and to receive intensity samples, as well as with an external microcontroller processor to deliver received data to an application. The transceiver is this kind of the analogon of a radio chip. Implementing appropriate demodulation logic comes with a set of considerable challenges, which we discuss in detail in the paper. We implement the transceiver in about 500 lines of C code that run on a microcontroller. We've got ports for two platforms, one STM32 based, another for the BeagleBone Black. For the BeagleBone, we don't implement the transceiver on the main ARM core, but use one of the real-time core processors on the board instead. We only use the heavy-duty ARM core because it gives us a convenient Linux interface for monitoring and evaluation purposes. We then attach the processor hosting the transceiver to the dense VLC hardware platform referred to on the slide, which gives us electronic circuitry to drive LEDs and retrieve intensity samples from a photodiode. We then take 25 of these nodes and set up a mesh network with them in our lab. The dimensions of the testbed, illustrated on the slide, and the relative positions of nodes within it are chosen to easily investigate zero-wire scaling behavior. In this presentation, though, will suffice with a brief high-level overview of zero-wire's performance. Detailed scaling analysis can be found in the paper. Let's start with latency. End-to-end latency across the optical mesh looks pretty much exactly like latency on a wire. Namely, it is directly proportional to the amount of data to be transmitted and the modulation speed that's being used. Latency is also virtually deterministic. For a given bus speed, it doesn't matter what endpoints you pick and how many hops they're apart. The time it takes for a frame to propagate between any two traffic endpoints is deterministic down to tens of microseconds. In terms of absolute performance, we can get 2 bytes of payload across 4 hops in less than 1 millisecond. Reliability then. The probability that a frame being sent across the network gets delivered intact to any node is about 99%. The most important caveat here is that zero-wire should stick to frames a few bytes in size. Symbol-synchronous buses tend to have a much stronger relationship between frame length and reliability, preferring shorter frames. If we increase bus speed beyond 20 kilobits per second, reliability will also collapse very quickly, because symbol synchronicity cannot be maintained. The good news, however, is that reliability proves to be contention agnostic. If 2 messages are being transmitted concurrently, the one with the highest priority gets through with the same probability as in the absence of such contention. This property carries over directly from wide buses such as CAN or I2C. Considering good put, we get 19 kilobits per second out of a 25-node network when modulating the bus at an optimal rate of 20 kilobits per second. This leaves us with a contention-agnostic network utilization of 95%. The remaining 5 are eaten up by frame losses and per-frame overhead. Again, from a good put perspective, 128 to 256-bit frames are optimal, leaving us with frame sizes and interaction patterns that are much more reminiscent of those found in CAN bus, for example, than in conventional wireless mesh networks. That brings us to the end of this presentation. In it, we introduced symbol-synchronous buses, a novel networking paradigm that makes an optical wireless mesh network behave as if all nodes in it are connected via a single wire. We then demonstrated empirically that the paradigm unlocks a performance envelope that so far has remained exclusive to wide buses by designing the zero-wire platform. Zero-wire, for example, showcases sub-millisecond end-to-end latency across multiple hops for frames a few bytes in size. At this point, 2 major questions remain. The first is just how far we can push zero-wire's performance. At this point, all of the signal processing is done in software, while mature networking technologies would use custom silicon for this kind of thing. It is this signal processing that currently bottlenecks zero-wire's performance. A similar argument applies to the transmission and reception circuitry. We simply took it from another research project on wireless optical communication. It is in no way designed for what we try to achieve in this paper. The second open question moves up the stack. What we have right now is a low-latency mesh network bit pipe. How to best exploit its performance from a protocol or application point of view remains to be addressed, along with the security implications of symbol-synchronous transmission and low-power considerations. Thank you, and make sure to check out our demo later today.